All right, how you guys? You are about to get your honors lesson on factoring special cases. So there are two special cases of factoring that you're going to need to be able to identify, and these will serve as shortcuts to you. So pay attention for patterns. We'll do just a few, and then I will teach you the official difference of squares, factoring pattern, and the perfect square trinomial. So these are patterns we've seen a little bit in class, but we're just going to focus on them more in these examples. We're going to factor the way you guys learned to for our first few examples. So 25x squared minus 1. So if you remember, this with only two terms means it's missing an x term. So I'm going to put the x term in there as 0x, then minus 1. And then we can go ahead and approach this the same way we have with all our others, which would be starting with that area model. So we know that our 25x squared goes down in the bottom left-hand corner, and our -1 in the top right. Then these other two boxes of our area model, we know need to add up to our 0x's. So we'll start our diamond. They need to add to 0x, but multiply to the same product as this diagonal. So -25x squared. So if we are adding two terms together to get 0x, that just means they're going to have to be opposites of each other. So a positive and a negative of the same thing. And if the product is -25, then it's pretty simple to see that those two terms are going to be positive 5x and negative 5x. So when we plug those into our area model, we've got 5x times 5x to get 25x squared. 5x times 1 is 5x, and 5x times -1 is -5x. So now we've got our factored version of this quadratic, which is 5x plus 1 times 5x minus 1. All right, let's look at another one. This one, part B, we do see three terms. Again, we're just going to start right off with the area model. We've got x squared in the bottom right, 16 in the top left. And we know our 8x's need to be what the sum of our other two boxes are. So we need to add to 8x and multiply to 16x squared. So the two numbers that do both of those, that would be 4x and 4x. So we've got our x squared here, x plus 4 is 4x, and another x plus 4. So in this case right here, we have a length and width that are identical. In other words, this is a perfect square. So this would be x plus 4 squared. So we haven't labeled them yet, but what you've seen already is one example each of a difference of squares and a perfect square trinomial. So I'm going to do two more, and then we'll get to the shortcut. See if you guys can predict what that would be on these next ones. So before I jump into this one, we learned last class that the first thing we should do before we jump into factoring is just double check to make sure there is no GCF or greatest common factor. In this case, since I see a 3 out front of my x squared, I immediately check the other two terms to see if that's something we can factor out, which it is, which will simplify and help us factor completely. So when we factor the 3 out of 3x squared, it's just x squared. When we factor 3 out of 30x, that becomes 10x. And when we factor 3 out of 75, that becomes 25. So this 3 out front is going to be part of our final factorization. So I'm just going to set that on my answer line now so that we don't forget about it later. So that 3 is just going to be along for the ride the whole time and out front of our factored form. Then we can jump into the area model to factor the result after we factor that 3 out. So we've got x squared in the bottom left, 25, and we want those two numbers that are going to multiply to 25x squared and add to 10. So what are those two numbers that add to 10, multiply to 25? That's going to be 5 and 5. So 5x here, 5x here. So we see another perfect square, just like we saw in the last example. So we've got x plus 5 squared, and that comes after the 3 out front. So 3 times x plus 5 squared. And then one last of these two-termed quadratics. So I see only 2. I also see the 9 out front. So I'm just double checking. Can I factor anything out of both? Not at the moment. So we'll jump right into the area model. So we've got 9x squared down here and negative 100 here. Don't forget that there is a missing x term. So if it helps to rewrite this out as 9x squared plus 0x minus 100. So we know that our two missing terms technically need to add to 0x. So 0x, but they need to have the product of 9x squared times negative 100. So that is negative 900x squared. So we need the two numbers that have a product of negative 900 and add to 0. So 900 is a pretty large number to get as a product. Since they're adding to 0, we know that their two terms need to be opposites of each other. We can think of just covering up the zeros, and we know that negative 3 and positive 3 would multiply to negative 9 and add to 0. So we just tack on that 0, and we know that 30 times negative 30, add to 0 and multiply it to negative 900. So we'll fill in the rest of our area model, positive 30x, negative 30x. Then when we start filling in the length and width, we know that to get a product of 9x squared, that's going to have to be 3x times 3x. 3x times 10 is 30, and 3x times negative 10 is negative 30. So we've got our length and width as 3x plus 10 times 3x minus 10. This is very similar to the answer we got in part A, which was 5x plus 1 and 5x minus 1. So the two patterns I'm hoping that you are picking up on are these situations where we have only two terms, where we're missing the x term, and the factorization ends up being almost the same factor, 5x plus 1 and 5x minus 1. So the only change is that sign switches. The 5x and the 1 are the same. We saw that again down here in part D, 3x plus 10, 3x minus 10. Our initial quadratic here was a perfect square of 9x squared minus, not a perfect square, but 9x squared is a perfect squared, and so is 100. Two terms, the x term is missing, and that turned into 3x plus 10 and 3x minus 10. That is what we call a difference of squares. So the two that I have highlighted orange are differences of squares. It's called a difference of squares because the two terms that we do have are both perfect squares. So in other words, we can think of, if you can rewrite the quadratic like this, something squared minus something else squared, what is squared to get 25x squared? So don't forget that, I'm just going to jot this down up here. When you square something like 5x, when we square something, it's just multiplication by itself 2 times. So 5x times 5x. So we've got 5 times 5, which is 25, and x times x, which is x squared. So when you square 5x, you are squaring the 5 to get 25 and the x to get x squared. So if you can rewrite a quadratic as something squared minus something else squared, that is called a difference of squares, and it will always factor to whatever is being squared here plus whatever is being squared here times the opposite of that, 5x minus 1. So the official formula down here, if you have two perfect squares and you're finding, and it's the difference between them, a squared minus b squared, that factorization will always be a plus b times a minus b. And you can also write, it doesn't matter what order, it could also be a minus b times a plus b. So multiplication is what's called commutative, which means you can switch the order. It doesn't matter. We saw that again in part D. So again, if I see two terms only, that's always your first sign, like, could this be a difference of squares? The first term, again, it does have to be a perfect square. So if you can rewrite this quadratic as something being squared minus something else being squared. So we know to get 9x squared, you would have to factor, or sorry, you would have to square 3x. To get 100 squared, or 100, you're squaring 10. So the 3x and the 10 are what are being squared here, and that's how you get the factorization of 3x plus 10 times 3x minus 10. So if we look at these examples down here, it does not have, the first term does not have to be the x squared term. This is still considered a difference of squares. So again, let's rewrite it as the two things being squared. So 36 is 6 squared and 9x squared is 3x squared. So that means when we factor that, 6 would be what I would call the A and 3x would be the B. So this factorization would be 6 plus 3x times 6 minus 3x. So if we go back up to this final example here, again, if we can rewrite it, we know 5 squared is 25, and we know to get 4x squared, we would square 2x. So 2x and 5 are the two values, 2x plus 5 times 2x minus 5. So that is the shortcut for factoring difference of squares. We'll do this last one really quick. What am I squaring to get 81x squared? That would be 9x. And what are we squaring to get 4y squared? That would be 2y. So factorization here is 9x plus 2y, 9x minus 2y. So that is difference of squares. Again, when you identify those, it will be a quick shortcut from having to rely on the area model and diamond. The next one is the perfect square trinomial. So the perfect square trinomial, perfect square is the name of it because as we saw in parts B and C, these both factored into perfect squares, x plus 4 squared. So that would be a perfect square. And then this one as well. The 3 had to come out, but then after that, then it was also a perfect square trinomial, x plus 5 times x plus 5. It's called a perfect square trinomial. Trinomial just means 3 terms. So there are 3 terms in each of these quadratics, 1, 2, 3. So a 3-term perfect square. So that's why it's called perfect square trinomial. To find a perfect square trinomial, you want to look at the first term and the last term. So the first term of a perfect square trinomial is always going to be a perfect square, as well as the last term will always be a perfect square. That is not the only condition that has to be met to be a perfect square trinomial. The first term has to be a perfect square. So x squared is x squared, 16 is 4 squared. The middle term is always double of the product of the two things that are being squared. So if x is being squared and 4 is being squared, the product of those two things is 4x, and 8x is double that. So that middle term will always be 2 times the two terms that are being squared. So that's where the 8x comes from. We'll see that same pattern here. So once we factor out the 3, we can't identify this perfect square trinomial until we factor out the 3. Then we see x squared, which is a perfect square. We see 25, also a perfect square. And then 10x, when I multiply 5 times x, 10x is double that. So 2 times 5 times x. So that is how you will identify a perfect square trinomial. So let's get down to the examples down here. So we see 3 terms. Again, we're just like, before you jump into factoring now, start paying attention to looking for those perfect squares. So we know x squared is a perfect square. we know 49 is also the perfect square of 7 squared. And then the last step to double check, make sure you are looking at a perfect square trinomial is that middle term, these two terms, 7 and x, not the 49 and x, the 7 and x doubled. So 2 times 7x, which is 14x. Once you identify that, if we go back up here and check how those factors, once you identify that first and last term that are being squared, then those two things are the two terms of your factorization. So if x is being squared to get x squared and 4 is being squared to get 16, then x and 4 are the two terms of our factors, x plus 4 squared. And then we saw that here. We see x and 5 being squared to get these. So the factorization is just x plus 5 squared. So down here, if we see that we've got x squared and 7 squared here, and 14 is 2 times x times 7, then those two values, x and 7, are the two terms of our factors, x plus 7 squared. You do need to be careful though, because in an example like this one, number 4 here, and then I'll go back and show you the same thing in part F. You do need to be careful when you see a perfect square trinomial with a minus in front of that second term. It's not a problem. It just means that whatever is being doubled here to get that middle term, like we know the 7x was being doubled here to get 14, that means our term that's being doubled is negative. So pay close attention to that. What that means is, so we see that p squared is a perfect square. We see that 64 is a perfect square, but in order to get this negative 16, then that means we are squaring negative 8 to get 64. So that's an extra like little tricky step, because technically you can square positive or negative 8 to get 64, but it must be negative 8 if this is negative 16p, because that middle term now will be 2 times negative 8 times p. So that's where the p squared minus 16. P plus 64. So those two terms, p and the negative 8, that's going to be how these factor. So p minus 8 squared. And then this last one right here. So again, with the 3 terms, and you notice that first term is a perfect square, we're checking to see if the last term is a perfect square. 4x squared is a perfect square. You just need to be careful, because to get that, you would be squaring 2x. To get 49, we're squaring 7. However, we see that negative in front of the 28, and that is our sort of red flag that we should be squaring a negative number to get 49. And then this middle term will be 2 times the 2x times the negative 7. So that's where you get 2 times 2 is 4 times negative 7. That's where you get the negative 28. So this, again, the 2x is what's being squared to get 4x squared. The negative 7 is being squared to get negative 49, which means the factorization would just be 2x minus 7 squared. So these are your two special cases. Again, difference of squares, which will always have two terms, which are always perfect squares with a minus in the middle. There is no such thing as sum of squares. So if you see something like a squared plus b squared, this is not a special case of factoring. You cannot apply the same thing. This actually doesn't factor. So be careful. It's just difference of squares. And then we see those perfect square trinomials. So when you're factoring moving forward, you're always going to keep an eye out for those perfect squares to see if you can use either of these shortcuts. The rest of this honors assignment is just to do the 8 problems on the back of this worksheet. These are all either perfect square trinomials or difference of squares. I do want to see your work on this. For example, when you are factoring something like 4m squared minus 25, I just want to see this one added step to rewrite what am I squaring to get 4m squared, what am I squaring to get 25, so that I can see exactly where your terms come from. All right, that's it. Good luck, and let me know if you have any questions.